Well, so what I propose to discuss now is some alternative. So, next topic. Some alternative approach to the Yangian. But I need some preparation. Some preparation related to some basics of representation theory on the example of the general linear Lie algebra. So I will deal exclusively with the Lie algebra GLN, the complex numbers as usual. But actually, this fact holds in much more greater generality for arbitrary reductive Lie algebras, but let's restrict to the framework of GLN. So I want to explain now, or maybe to recall to somebody who knows already, what is the category O. So topic is category O. This notion was introduced by Bernstein, Gelfand, Israel Gelfand, and Sergei Gelfand. Let me explain what is this. The important feature of reductive Lie algebras, and in particular of GLN, is the existence of a triangular decomposition. Triangular decomposition of G. Let me recall it. So G is written as a direct sum of three subalgebras, but the direct sum only as vector spaces. And minus, and plus, and H. In general, H means the Cartan subalgebra, but in our concrete situation, it's simply diagonal matrices. So I recall that we have a canonical basis. Canonical basis of a matrix units. And so we have this picture of matrices. So these are the diagonal matrices. This is H, this is N plus, and this is N minus, meaning that N plus is the linear span of the generator such that I is strictly less than J, and minus is something similar, but with the opposite inequality, and H is the span of the diagonal matrix units. And the next evident remark is that N plus minus are nilpotent Lie algebras. Now let's denote by G mod the category of representations of G or G modules. G modules. This is a very large category. And I will introduce some smaller category inside it. One smaller, I will explain what it is. These are weight modules. and inside them sits the category O, some subcategory O, and inside it are finite dimensional weight modules always over G. So let's explain what these are. So G module is arbitrary modules. What are weight modules? So weight, so V. So let V be some G module. We say that it is a weight module. Weight module means the following. Our modules can be written as a direct sum of subspaces. Here mu are some linear functionals on the Cartan subalgebra. So the dual space to a Cartan subalgebra, and because we have a canonical basis of a diagonal matrix units, we can identify it to the coordinate linear space. And so we can write mu as an n-tuple of general complex numbers. And the elements of this space are usually called weights on the Cartan subalgebras. And this is the subspace of elements which are common eigenvectors with respect to the action of H of the corresponding weight. So this just means that U is the set, the subspace of vectors of our space, such that when we apply some basis element from our diagonal Cartan subalgebra to V, then we get this one. In I, for instance, this is in some example. So assume that we have a coordinate space is a tautological G module, because our real algebra consists of matrices, and the matrices operate on this space. So it is a G module, and each basis vector is an eigenvector. So it is a vector from a weight subspace. Maybe I should say it is weight subspace corresponding to a given mu. So here the decomposition is just a coordinate decomposition. And more generally, if V is some tensor power, then the weight vectors. So the weight vectors is a vector which belong to some of the subspaces, of the weight subspaces. So here the weight vector are precisely decomposable tensors. any tensor, any decomposable tensor is a weight vector. Okay, so this is the definition. This is the definition. We must have such a decomposition. One can say also the equivalent condition is that the Cartan subalgebra, acts by its action is semi-simple, which means that in principle it's a commutative Lie algebra. So in principle, one can imagine that it's some operators from H have some non-trivial Jordan blocks. So this must be excluded. Okay, so what is the category O? Oh, category O. I don't know why O. This is a well-established terminology. The category O means the following. V belongs to this category if, first of all, it is a weight model. Is a weight model. So we have this decomposition, some decomposition, and it is canonical. It's unique. It's a little exercise in linear algebra. And next, we have a following requirement for any vector from V. Let's apply to it the whole universal enveloping algebra of n plus. We apply arbitrary elements from this algebra to V, and the condition is that the dimension of this subspace should be finite. Usually one says that in this situation, one says that n plus acts locally nilpotently. Okay, so let's discuss what happens with this condition, how to imagine the structure, the rough structure of the models from category O. First of all, we have weight vectors which span the whole space. And next, let's analyze what happens if we apply some matrix unit to some weight vector. So assume that V belongs to some weight subspace, and we apply these matrix units, and it's easy to see that the result is contained in another weight subspace of the following type. Let me write it. I mean here that the canonical basis, canonical natural basis, in this coordinate space, which I identify with the due to the Cartan subalgebra. So this means that as a linear functional, if we apply it to some matrix unit, diagonal matrix unit, the result is the canonical delta. So this is, we have another basis, which, sorry, which is a basis in H. And what I said it just means that this basis is dual to this one. So it's easy to see that we have this condition. So when maybe it's convenient to introduce one more piece of notation, of terminology, we say that the from N plus, which means I, are raising generators, and those from N minus, which means that I are lowering generators. In what sense? We can introduce some partial order on the weights as follows. We say that if you have two weights, mu lambda, we say mu is smaller or equal to lambda if we have the following condition: the difference of mu lambda is equal to mu plus something like this. We have some coefficients, maybe. The condition is that these coefficients are non-negative integers. So in this terminology, we see that this weight is greater than this one. So applying the generators from N plus, we get greater weights, and applying the lowering generator, we get lower weights. It's not a linear order, but it's a partial order. But of course, there is some evident relation to the lexicographic order. So if you have this relation, then lambda is greater than mu with respect to the lexicographic order. This is evident from this picture, from this definition, and because these coefficients are non-negative. So what we have in general, what means the category O? Given a weight vector, it has some weight. If we apply some raising operator, we get some, we move, maybe it's better to write as follows. So we move to some weight space which is higher with respect to our order, applying some other raising operator. We move next level, and so on. The category O condition means that this process must stop at some moment, because the applying generator from N plus should produce a finite dimensional subspace. So at some moment the sequence must stop, so we must get to 0. So this happens to any weight vector. So this is the basic condition. The basic condition, and one more definition is with highest weight. Highest weight module. What this means? This means the following. First of all, V must be in the category O. Next, it should possess some vector. There exists some vector which is in some weight space, such that it is annihilated by all raising operators. So one can say that V is annihilated for any pair I less to J, which means that V is the annihilator. The invariance with respect to the algebra means that this is the subspace annihilated by the action of this algebra. And the last condition means that V is cyclic, which means that if you apply the whole algebra to our vector, that we get the whole space. So in general situation, this object is always a submodule, and we require that this submodule should coincide with the whole module, which is the cyclicity condition. So highest weight means the existence of such a vector, which is highest weight, which this means this condition, annihilation by n plus, and cyclicity, which means that we get this condition. Okay. So we are interested in highest weight modules. What are some basic, so maybe some questions at this moment? Any questions? Okay. Well, some simple remark is as follows. So we say that this lambda is the highest weight module, and this is justified by the following fact, that we have the lambda has dimension 1, and all weight subspaces with mu distinct from lambda satisfy the condition are smaller. Why this happens? Look, let's look. We have the decomposition. The whole universal enveloping algebra can be written as the product of 3 subalgebras minus the Cartan and n plus. This is a direct consequence of a triangular decomposition. So what happens when we apply this to our vector? If we apply this part, it is annihilated except the action of 1. So we have the following. Applying, so if you assume V is the highest weight vector, highest weight vector. So if we apply, this is the same as applying, because the only non-zero contribution comes from the scalar elements from this object. And next, applying this also does not produce anything new, because the Cartan subalgebra preserves our vector. It is a weight vector. So we can write, and this is the same as apply n minus. What happens with n minus? If we apply the identity, we get again V, and next we can apply the generators, and they shift the weight below. So we get only the weight subspaces which satisfy this condition. So this can be written, we can depict it as follows, something like this. Here we have the weight lambda, and next, so this picture I am trying to represent what happens when we apply some lowering operators. We get something below with respect to our special order. So we have some kind of cone. So here are some possible weights which appear in the weight decomposition of our model. And this weight, so this weight is canonical. It is really the highest weight of our model. Next, it's useful to know the following facts. So for any weight, so I call the coordinate space, for any weight there exists some universal highest weight model, which is called the Verma. Let's denote it as it is defined as follows. We say that M lambda is can be identified with the universal unavailable algebra modulo some ideal, some left ideal generated by the elements of the following type. First of all erasing elements, and next also diagonal elements minus this one. So this is a scalar. One could add, but it's not necessary. So what I try to say, if we have some highest weight module with its highest weight vector, then this vector is annihilated. It is annihilated by any generator, and any elements of this kind by the very definition, because it is a weight vector with respect to lambda, and hence it is also annihilated by the left ideal generated by these and these elements. In principle, the annihilator of our model could be large, but the universal object is obtained by restricting the annihilator to exactly this left ideal. And it's easy to see that it is cyclic by the very definition. So this is a vector space. Because it is a quotient by a left ideal, our algebra operates on it on the left, so we get a module of this algebra, and this is the Fermat module. By the very definition of this module, we have the following picture. So I hope it's clear. If V is the highest weight module of a given weight V, then it follows that there is a canonical morphism of modules V, which is morphism is modules and preserves the highest weight vectors, and it is unique up to multiplication by a scalar. So this is by the very construction, because if you have such a module, then the annihilator of our highest weight vector should be some left ideal, which in principle which must contain strictly or coincide with this ideal. And from this we deduce this fact. So if we take the quotient by large ideals, we get such a row. Is it clear at this point? No, please ask. So this is called the universality property. Any highest weight module is covered by the Fermat module. And also there exists a unique for any other, there exists a unique, irreducible quotient. So it is another highest weight module such that we have this map should be surjective because the highest weight vector is cyclic, and it is irreducible or equivalently a simple module. How it is obtained? The idea is very simple. We take all proper submodules in the Fermat models. And then the sum of all, in this family of all proper submodels, there exists the largest one. Why? Because we simply take the sum of all submodules, proper submodules. But proper submodules means that the weights of these submodules do not contain lambda, because if submodule contains the highest weight, this submodule should coincide with the whole modules. And because there exist maximal proper submodules, so we can take the quotient over it and we get this lambda. And the general picture is the following. Generically, a lambda is the same as a lambda. For a generic lambda, the Verma model is already irreducible, simple. But in some special, for some special values of lambda, the picture is not very simple. It requires some analysis. We get the Verma model is already reducible, and then there exists a proper quotient, which is a lambda. So in particular, let me, I will explain it a bit later. Any finite dimensional model is any finite dimensional irreducible model should coincide with some lambda, and it is then a proper quotient, because this Verma model is infinite dimensional by the very definition. Its size, the size of n lambda, is the same as this universal envelope algebra. Why? Because this is a consequence of Poincaré-Birkhoff-Witt. When we take this quotient, this one, from the Poincaré-Birkhoff-Witt, this means that we kill from this decomposition. This just means that we kill this component and only this one remains, and exactly this one remains. Maybe it should be written as follows. Let me write it in more detail, which means as follows. Excuse me. Poincaré-Birkhoff-Witt implies that our algebras can be written as a direct sum plus the left ideal, just this one. I don't want to introduce some special notation. Let me mark it. Left ideal, this one. And so after factorization, after taking the quotient, we exactly get this as a subspace. So as a subspace, the Verma model can be identified with infinite dimensional space. Okay, so maybe again, let me ask if there is some questions. Should I explain in more detail? No?
Why U of n minus cannot intersect this ideal?
Let me explain again. Let me explain again. So what we have U of G can be written as follows. Let me write as follows, plus or maybe in more detail. Maybe in more detail. So we have a basis in U of G consists of monomials like this. Some product in some prescribed order. Next, we have some product diagonal and some product of raising generators. But we also have the scalars. So we also have one, which is a part of this picture. So any element of our algebra can be written uniquely if we choose some order on the generator as a product of such and such monomials and maybe some constant term. But we want to transform this picture, and we want to say that we have something like this. Okay. Next, we have some, how to say, I'm sorry.
I think I understood why classes of...
It's easier to understand than explain. I'm sorry. So the idea is just to slightly rewrite this fact by subtracting some constants in order to get some elements which kill the basis, the highest weight vector, which are contained in our ideal, and what remains are exactly some non-trivial products of the lowering. No, one is also allowed. I'm sorry, excuse me. Maybe I should explain it better, but the idea is contained here.
Okay, thank you.
Sorry. The next topic I want to explain is very important for the whole story. It is called the Harishchandra homomorphism. a simple but very important construction. Again, it's general. It's applicable to any reductive Lie algebra, but we restrict our attention to G11. So again, G is G11. And let's examine the centralizer of a Cartan subalgebra. So what this means, the Lie algebra operate on itself by the joint representation. I call what this is. We take the commutator. Hence, it operates on the universal undeveloped algebra using the Leibniz rule. We extend this operator from G to universal undeveloped algebra the usual way. Using the Leibniz rule, if you have a product, then we apply the commutator to each of the terms. So this is exactly the weight 0 subspace with respect to this action, or simply this is the centralizer. It means that this is subspace of elements which commute with all diagonal matrix units. So this is subspace of X in the universal such that is 0. It's a subalgebra. And the following remark, any element of the centralizer is a linear combination of monomials. This is a general effect. So write it. Let's consider monomials. A monomial. It is a weight vector with respect to the action of the Lie algebra on the universal undeveloped algebra. But what is the weight? So the weight is as follows. No, it's correct. I'm sorry. So it implies the following. So if the weight is 0, it implies that the the number of raising operator is equal to the number of lowering operators in this product. Is it clear or not? Because the weight, the whole weight, is equal to from this we conclude that if you have, and we always we can assume that we always can assume that the raising generator are on the right, the lowering are on the left, and the diagonal in the middle, for instance, it's not so important. And if a weight is equal to 0, it means that we have some balance. The number of the raising operators, which are on the right, should be balanced with the number of lowering operator on the left. Is it clear or not?
Я что-то, видимо, не проснулся. Нет, непонятно. Вроде можно... Ну, общий вес должен быть 0, но почему должно быть столько же повышающих, сколько понижающих? Ну, вот казалось бы... Ну вот прямо в GL3 вот я возьму один оператор E1,2, один оператор E2,3 и один оператор E3,1.
Ну, хорошо, давайте возьмем.
Сейчас я прошу прощения, что-то
Так, давайте посмотрим.
запутался. Ну, произведение нет. Произведение этих товарищей.
Это я понимаю, да.
Да.
Но веса складываются при этом.
Веса складываются, да. Ну вот...
Значит, смотрите, значит, что у нас тогда получится? Значит, мы должны взять такой вот вес. Это вот то, что происходит отсюда. Сложить с таким весом. Так. И сложить вот с таким весом. Мы их складываем. Здесь получается 0. Здесь минус 1 получается. Здесь получается 0.
Нет, 0.
Да, пожалуй, что так. Да, это я отдал Маху, да. Но, во всяком случае, верно вот что. Это неправильно. Это неправильно. I'm sorry, this is incorrect. Но должно быть верно, во всяком случае, следующее, что если... What is correct? What is correct? If contains raising generator, then it also contains a lowering generator and vice versa. Do you agree? Согласны вы с этим?
Это уж несомненно.
Потому что если у нас будут только повышающие операторы, а понижающих не будет, то мы веса 0 не получим. Почему? Потому что мы двигаемся вверх, у нас может быть вес 0, так? Мы двигаемся вверх хотя бы по лексикографическому порядочку. Значит, если мы уже на что-то сдвинулись вверх и вниз никак не опустились, то мы уже от нуля ушли. Так что это я проврался. Да, это я проврался. Уже чувствовал, на самом деле, что вру. Вот, но вовремя не остановился. Спасибо, что вы меня поправили. Вот это вот верно. Тут уже точно. Тут уже точно. Что мы теперь, what I want to say. There exists homomorphism from this centralizer to this object, which is the same as the symmetric algebra, because the Cartan subalgebra is commutative. There is no difference between the universal and the algebra and the symmetric algebra. And these are simply polynomials. Polynomials on the dual space, on the weight space. So how it is constructed?
So, sorry, it's a homomorphism of representations, not of algebras, right?
No, homomorphism of algebras.
Ah, okay. Thank you.
Algebra homomorphism.
And the left is also commutative? Or maybe... Is this true that U of G...
Commutative. It's not commutative. This is commutative. It's not commutative.
Ah, so this is like not embedding. Okay.
Not
Okay,
embedding.
thank you.
It's surjective, but not injective. What is this construction? And this is the Harishchandra homomorphism. Harishchandra is one person, not two. So what is the definition? The definition is as follows. So let's denote by I plus, the left ideal U of G generated by n plus. So a monomial, let's use monomials where the raisings are on the right and the lowering on the left. So in this picture, the monomials which are in I plus are those which have at least one raising generator, which is always on the right. And likewise, it is the right ideal, generated by n minus. And now we have the following claim. When we take the intersection of our weight zero elements with I plus, this is the same as taking intersection with I minus, because if you have a raising operator, we always have a lowering operator on the left and vice versa. So these two intersections are the same. This follows from the previous step. Okay. But this is a left ideal. In the subalgebra as an intersection of a left ideal in the algebra with this subalgebra. And this is a right ideal. And because these and these are the same, this subspace, this object is a two-sided ideal. So this is two-sided ideal a very nice argument, of course. And because it is a two-sided ideal, we can take the quotient. So take the quotient. We have an algebra morphism quotient with two-sided ideal. But now I claim that this quotient is the same, can be identified with this one, because we have a direct sum. Again, we have by Poincaré-Birgouff-Witt. It implies that U of G is the direct sum plus the we have this. And this, by the very definition, what is also important, that the subalgebra is contained. Because it's clear that it commutes with H, with itself. So this map is defined simply as a projection onto this subspace. And this projection is the same, we can write the same with this one, so this is our two-sided ideal. So this projection is factorization modulo a two-sided ideal, hence it is an algebra morphism. So is it clear or not? So the key idea is contained here. This balance should hold. This is the Harishchandra map. And next we have what is called Harishchandra isomorphism. What is Harishchandra isomorphism? Let's consider the center of our algebra. It is contained in this centralizer, but it's smaller. And the claim, this is theorem, which says therefore the restriction of Harishchandra homomorphism to the center is injective. So it's a commutative algebra, the center. So under the Harishchandra map, homomorphism, after restriction to the center, we get an injective map. How to prove this? There is a general proof which works for, it's not evident, it's a non-trivial claim. One can prove it for any reductive algebra, and you can find it in some textbook, maybe Humphreys or Dixmier, maybe in what I forgot, Fulton Harris maybe, but I'm not sure. But in our special situation of GLN, it's a consequence of Perelomov-Popov map, Perelomov-Popov theorem, why it is injective. And let me continue. This is only one claim. And the second claim is the image of the under Harishchandra is the algebra of shifted symmetric polynomials. I forgot if I introduced this notation. But let me introduce it. So first of all, these are, in my notation, these are symmetric polynomials. Symmetric polynomials. Polynomials in n variables. N variables. Let me write then this. No, it's not a good notation, sorry. Next. And sim star, it's not the dual space. This is the old notation from some old paper. These are shifted symmetric. Shifted symmetric polynomials in the same variables, and shifted symmetry means that symmetry with respect to some shift, some change of the coordinates, respect to new coordinates, where I assume that this is equal to the x plus any constant, but any fixed constant, minus I for some and then any fixed constant c. So if we make this change of variable, we must get a symmetric polynomial in the new variables. So in my old notation, previous when I discussed Perelomov-Popov, I use the coordinates and the coordinates instead of the x's and the y's, and I wrote I to be equal to I plus n minus I. So the constant c was n, but actually nothing changed if you use some other constant. This is the question of convenience. You can take any constant you want. So let me recall that we showed actually what we showed. We showed that the center, we just used implicitly, we just used the Harish-Chandra homomorphism. Why? But because we applied the central elements to the highest weight vector, to a vector which is annihilated by the raising coordinate. Because we know that the central element operate by scalar in any irreducible model. So this is, let me explain this in more detail. I forgot to mention the following lemma. If V is the highest weight the center operates on V by scalar operators. Why? It's true. And moreover, if A is in the center and say I bar is the image of A by the Harish-Chandra map, so this is an element of this universal algebra. And when we apply, so what we have, when we apply A to the highest what happens? So first of all, we know that applying n plus to V we get 0. By the very definition of a Harish-Chandra map, which means that A applied to V is the same as A bar applied to V, because the difference between A and its image under Harish-Chandra is contained in the left ideal generated by n plus, and n plus kills our vector. And next, because A bar is contained in this subalgebra and V is a weight vector, so we get some scalar. Complex number. And because, so we see that we have some, so this implies you have some algebra morphism. From the center to a field of complex number. This is an algebra morphism. This follows from the fact that the Harish-Chandra map is an algebra, is multiplicative. Is it clear? Not? Please ask. Okay. And moreover, we also have that A operates as the scalar operator on the whole space V. Why? But because our space V is obtained by applying some elements of Lie algebra, of a universal undeveloped algebra to the highest state, which is a cyclic. But because it is in the center, it commutes with the action of the algebra, and this reproduces the same scalar. This scalar is reproduced if it remains intact if you apply any algebra element to V, because these elements can be put on the left. Is it clear or not? So we get that the central elements operate by scalars. This is clear from the Schur lemma, if you know that our model is irreducible. But more generally, it holds for highest weight models, which in principle can be reducible. This can happen. This is a little bit more general fact. So what this means? This means that we get a map. So we get a map. You get multiplicative. Let's call such a map from algebra to the field of complex number, a multiplicative functional, because it's a linear functional, but it is also multiplicative because it is compatible with the multiplication in this commutative algebra. So we get multiplicative functional. Let's put it here. From the center to the complex number. But the next observation that depends only on the weight, and not on V. So in principle, it may happen for generic lambda that there are some distinct highest weight modules with the same highest weight lambda, which this exactly happens if the Fermat model is irreducible. In this situation, it is unique. It is unique highest weight model. But it may well happen that there are some number of distinct highest weight modules with the same lambda. But in this situation, the claim is that its multiplicative function does not depend on the specific model. It depends only on the highest weight. And this is again a consequence of Harish-Chandra homomorphism. Why? Because we have this picture. To find. Oh, this picture. So the claim is the action of our central element depends only on the projection, coincides with the action of this component, this projection. But the action of the Cartan subalgebra depends only on the weight lambda and nothing more. So what we get that for any conclusion is for any lambda, which is a function on which is an element of H star, we have a multiplicative linear function. I write as follows, because it depends only on the weight from our center to C. And again, this can be rephrased as follows. Oh, sorry. As follows. We have a map from Z to some functions on Cn. And what are these functions? But we calculated this function exactly in the proof of Perelomov-Popov by Perelomov-Popov theorem. We know that the image is the subalgebra, what I denote as follows. These are polynomials, not arbitrary, some general functions in lambda, by polynomial functions. Polynomial functions in which are symmetric in the shifted variables. So these are shifted symmetric polynomials. And it seems that I proved that the algebra, the center, is an algebra of polynomials in n variables. It is, how to say, it is, okay, so I proved that the graded algebra associated with the center as a filtered algebra is isomorphic to the algebra of symmetric polynomials. And this implies that this map, the map I have in mind, is actually an isomorphism of a center on the algebra of shifted symmetric polynomials. We have to be sure that the kernel is zero, but we know because, remember, using the graded algebra trick, we can reduce this claim to the fact that any polynomial on the space of matrices, which is invariant with respect to conjugation, depends only on the eigenvalues and depends symmetrically. Using this fact, we can conclude with this map. This map is injective. Okay, I should stop at this moment. And let's discuss after I switch off